Hello everyone, I am R. Kailasham, a PhD student at the IIT Bombay Monash Research Academy, and I am currently in the process of writing up my thesis. I am jointly supervised by Professor Rajarshi Chakraborty at IIT Bombay and Professor Ravi Jagadishan in Monash University. Here are our email addresses for correspondence, and we'll be happy to answer any of your questions. I'm going to be presenting some of our recent work involving simulations on polymer models with internal friction. So, what exactly is internal friction? Conformational transitions in polymer molecules are impeded not just by solvent molecules but also by intramolecular interactions whose effects are collectively referred to as internal friction or internal viscosity. This phenomenon has observable macroscopic consequences as evidenced by the two examples shown here. For example, the folding time of a protein molecule is plotted as a function of the solvent viscosity here. In the extrapolated limit of zero solvent viscosity, where one does not expect there to be any external resistance to folding, there is still a finite intercept which indicates the presence of internal resistance to folding. Similarly, in the forced unfolding of peptide molecules, it is observed that the work dissipated in the process is much greater than what could be explained due to the solvent friction alone, thereby hinting at the presence of internal modes of dissipation. Clearly, internal friction has a wide ranging impact and it is of fundamental importance to understand this better. The way we do that is through Brownian dynamic simulations of the bead spring dashpot model. The springs here of stiffness H represent entropic elasticity, and the dashpots of damping coefficient K provide the rate dependent restoring force that is characteristic of internal viscosity. The total force in a connector vector has contributions from both these elements, and we have considered a Hookean force law in the connector vector. Internal friction is quantified using the phi parameter, which is the ratio of the damping coefficient of the dashpot to the bead friction coefficient. You would sometimes also see the symbol epsilon being used to denote internal friction. Now, before proceeding to explain our solution methodology and our results, I would like to quickly brief you about typical rheological measurements. The polymer solution is confined between two parallel plates, with the top plate moved as being shown here. This results in the setting up of a stress in the confining fluid, which is represented using the stress tensor, which has the following general structure as mandated by symmetry and conservation of angular momentum concentration in simple shear flow. It is possible to define three material functions based on the elements of the stress tensor. Eta P, or the shear viscosity, is the force per unit area required on the top plate to move it at a shear rate of gamma dot. Polymer solutions are viscoelastic and also possess finite values of the normal stress differences, and these are characterized using psi 1 and psi 2. In a different experiment, the bottom plate is held fixed while the top plate is oscillated at a frequency of omega. The resultant shear stress is also seen to oscillate at the same frequency omega, but is offset by an angle phi due to the viscoelasticity of the polymer solution. By fitting a cosine curve to this data, it is possible to obtain two material functions, eta prime and eta double prime, with eta prime characterizing the viscous or the liquid-like response of the solution, and eta double prime characterizing the elastic or the solid-like response of the solution. The machinery for the solution of bead spring models with internal friction, without internal friction is fairly well established. One begins with the force balance on the beads, requiring that the sum total of the hydrodynamic drag force, the random Brownian force, and the spring force all add up to zero. One then obtains an equation of motion for the connector vector velocity, which is combined with an equation of continuity to obtain a Fokker-Planck equation, and its equivalent stochastic differential equation is integrated numerically. The inclusion of internal viscosity, however, causes a problem because it results in a coupling of the connector vector velocities, as indicated here. Under such circumstances, it is not obvious how the Fokker-Planck equation and the governing stochastic differential equation may be obtained. We have addressed this knowledge gap, and I'll be talking about this in more detail. I would like you to note that the connector vector velocities in this case are explicitly coupled only to their nearest neighbors. The inclusion of hydrodynamic interactions would result in an explicit one-to-all coupling of the velocities, and we are ignoring it for the moment. The question of removing the coupling of velocities has been taken up in great detail by Mankey and Williams, who have provided a general three-step procedure for obtaining a decoupled expression for a scalar Sj that depends on Sj minus 1 and Sj plus 1. As the first step of the procedure, expressions for S1 are substituted into S2 and so on till the end of the sequence. This removes all backward coupling and gives an expression for Sj that depends only on Sj plus 1. Similarly, in the backward substitution process, expressions for Sn are substituted into Sn minus 1 and so on till the end of the sequence. This results in the removal of all forward coupling and gives an expression for Sj that depends only on Sj minus 1. After a simple change of variable as indicated here, the expressions from steps 1 and 2 are combined together to get a decoupled expression for Sj. Let us now take a look at what the generating equation for our case looks like. Since Sj is mandated to be a scalar, we have taken a dot product of the connected vector velocity with Qk. At this point, I would like to emphasize that while we have borrowed the decoupling machinery from Mackey and Williams, we differ significantly in the actual equation that's being subjected to the decoupling. You can understand this better by looking at the right-hand side of this equation, where the dashed and the solid underlined terms refer to the Brownian force terms and the spring force terms respectively, and these two forces balance each other exactly at equilibrium. Markey and Williams were interested only in the calculation of the stress jump, which is a linear viscoelastic property, and had consequently neglected both the underlying terms. We, however, are interested in a general solution that is valid both at equilibrium and in flow, and have retained both these terms in our analysis. And this has led to a steep increase in the amount of algebra. After performing the necessary calculations, we arrive at the following governing stochastic differential equation for the bead spring dashpot system. Using the Gieseker's formula, we are also able to derive a stress tensor expression for the system. And we do this based on the recommendation given by Schieber and Oettinger, who have observed that this choice results in a thermodynamically consistent stress tensor expression. As an aside, the highlighted terms indicated in both these equations may also be evaluated analytically by using recursive function representations of continued fractions. Having obtained the governing equations, we now proceed to evaluate a few rheological quantities of interest. Plotted here is the shear viscosity as a function of time at the inception of simple shear flow in a 3-bead chain with internal friction. An important consequence of internal friction is the appearance of a discontinuous jump in stress at time t equal to 0, and this is called a stress jump. And this is absent in models without internal friction, as shown in the inset here for a Rouse chain without internal friction. The stress jump is evaluated by fitting a polynomial to finite time data and extrapolating it to the limit of t equal to 0. Shown here are the evaluated stress jumps for a variety of chain lengths at a fixed value of the internal friction parameter. And we notice, first of all, that the stress jump is independent of the shear rate, and this is in accordance with the theoretical predictions of Gerhardt and Mankey. Furthermore, the stress jump is also seen to scale linearly with the chain length. The lines in these two figures are semi-analytical approximations by Mankey and Williams, who have also assumed that the terminal beats and the interior beats contribute equally to the stress jump. It is seen that their approximation performs remarkably well when compared to the exact PD simulation results. Having obtained the governing equation and validated it, we are now in a position to ask two questions. Firstly, what do the material functions for chains with internal friction look like in simple and oscillatory shear flow? And secondly, how important are fluctuations in the treatment of internal friction? We are particularly drawn to the second question because the state of the art for interpreting the effects of internal friction from biophysical experiments relies on a pre-average treatment of the phenomenon where the projection operator is replaced by its equilibrium average quantity. Let us now address these questions in turn. Shown here are the eta prime and eta double prime data for chains with internal friction of various lengths and a fixed value of the internal friction parameter. A striking consequence of internal friction is the appearance of a high frequency plateau in eta prime, which is absent for the Rouse case where eta prime is seen to asymptotically go to 0 at high frequencies once the solvent friction has been subtracted off. It's been shown theoretically by Gerhardt and Mankey that the value of this plateau is numerically equal to the stress jump. Since the stress jump scales linearly as the chain length and the Rouse viscosity with which we normalize this quantity scales as the square of the chain length, eta prime over eta r, when plotted in this way, the height of the plateau diminishes with the increase in chain length. With respect to eta double prime, it is seen that the inclusion of internal viscosity does not change the Rouse scaling. Particularly in the intermediate frequency regime, there's the appearance of a plateau for the 10-beat case whose exponent has not quite reached its asymptotic value. With the increase in chain length, we however expect that this value would be reached. In both the figures, it is seen that the semi-analytical approximations by Mankey and Williams, as indicated by lines, perform better with an increase in chain length, when compared to the results indicated by the symbols, which correspond to the exact VD results. Let us now turn to the material functions in simple shear flow. Shiba and co-workers have shown, based on Gaussian approximation studies on dumbbells, that internal friction does not affect the zero shear rate properties. We are in concurrence with this prediction in our case as well. There's a striking similarity between the variation of viscosity for chains with IV and chains with hydrodynamic interactions in that they both show a shear thinning followed by a shear thickening. There is a notion in the literature that in the limit of infinite internal friction, one approaches the rigid rod limit. However, our viscosity data at least contradicts this expectation because while bead rod chains show a high shear rate plateau in the viscosity, there is no hint of a plateau formation for the viscosity of chains with internal friction. Next, we turn to the first normal stress difference coefficient, where the chains with internal friction predict the appearance of a high shear rate plateau for psi 1. This is in stark contrast with the hydrodynamic interaction case, where one observes a shear thinning followed by a shear thickening. Furthermore, this is also in contrast with the bead rod chain behavior, where one observes a continuous shear thinning. Since psi1 is a readily accessible quantity experimentally, we anticipate that the measurement of psi1 would enable the rheological quantification of internal friction. Let us now turn to the question about fluctuations. The pre-average model introduced by McLeish and co-workers and its variants are attractive because of their analytical tractability. We'll examine the importance of fluctuations on the autocorrelation of the end-to-end vector because this is important for the calculation of quantities like the folding or reconfiguration time. We'll also compare the two model predictions for their viscometric predictions. Shown here is the autocorrelation of the end-to-end vector for chains of different length and two values of the internal friction parameter. The symbols are exact BD simulation results on the fluctuating IV case, and the lines are pre-average model results. In both the cases, it is observed that the difference between the two model predictions diminishes with an increase in chain length. What this implies is that for the calculations of folding or reconfiguration time, it is okay to use the pre-average model provided one uses a long enough chain. However, in the presence of a flow field, there's a significant difference in the two model predictions. We have been able to derive analytically an expression for the transient evolution of viscosity for chains with pre-average internal viscosity. And we have validated these results by comparing against BD simulations on chains with pre-average internal viscosity. So the lines in these figures are the pre-average results, and the symbols are BD simulation results on chains with fluctuating internal viscosity. While both models predict the occurrence of a stress jump, they differ in their magnitudes of the stress jump. Furthermore, the qualitative trend in the evolution of viscosity is also different for the two models. Let us now look at what the steady shear predictions look like. I have already shown data for the steady shear viscometric predictions of the fluctuating IV model, but I'm showing it again here to emphasize its difference from the pre-average IV case. While the fluctuating IV case predicts a non-monotonous variation in the viscosity, the pre-average IV case predicts a constant value of the viscosity, which is equal to the Rouse viscosity, at all values of the shear rate considered and is independent of the internal viscosity parameter. So in conclusion, we have solved exactly the bead spring dashpot chain model by expanding the scope of an existing decoupling methodology. We have also derived a stress tensor for chains with internal viscosity and therefore have been able to obtain material function predictions in simple and oscillatory shear flow. We have also established the importance of fluctuations in the treatment of internal friction. While it is known that hydrodynamic interactions significantly affect the dynamics of polymer chains, we are therefore interested in observing the effects of internal friction and hydrodynamic interactions in the chain model. I would like to acknowledge the computational infrastructure at both IIT Bombay and Monash University and thank National Computing Infrastructure Australia for the CPU time grants. And I'm also grateful to the IITB Monash Research Academy for their funding and general support. Our coordinates are given again here, and I look forward to fielding your questions in the interaction session.